Hello everyone, I'm Mark Galoppo, a PhD candidate at the University of Canterbury under the supervision of David Wiltshire, and I'm going to talk to you about my research in finding an exact solution for differentially rotating galaxy model in general relativity. So let's start by discussing the problem. The problem in this case is dark matter. Dark matter is a very simple hypothesis that remarkably explains a plethora of astrophysical and cosmological observation, from galaxy rotation curve to gravitational lensing to cosmic structure formation in the early universe. However, after billions of money, billions of dollars invested, and almost 4 decades of research, direct detection still eludes the scientific community. Therefore, we can ask, are we perhaps missing something? Are we estimating the amount of dark matter in our universe, galaxies, badly, for example? Are we off by some amount? Well, to see where we're going with this, let's review the system we're talking about. All the systems in which dark matter presence has been informed are in a low energy regime, which means that we're talking about subrelativistic local velocity and weak gravitational potential that cannot accelerate the components of the system to relativistic velocities. Now, in such system, general relativity, our accepted theory of gravity, is assumed to reduce to just Newtonian perturbation over a Minkowski background, fixed Minkowski background. Therefore, what we're saying is that we're using Newtonian gravity, essentially, to estimate the amount of dark matter present in galaxy clusters, and so on and so forth. Now, is this okay? Should we question this? Well, strictly speaking, the low energy regime limit of general relativity does not boil down to Newtonian gravity. We can just think of gravitational waves or geons, for example. They are, or frame dragging. We have a lot of general relativistic low energy effect which have no Newtonian analog. Mathematically speaking, this difference arises from the fact that general relativity is a highly nonlinear theory, while Newtonian gravity is linear theory. In GR, the space-time, the gravitational field, carries angular and linear momentum and energy, in stark contrast with the Newtonian non-dynamical field. These mathematical nonlinearities, from a physics point of view, mean that, well, when we take averages of motion of matter, we are really accounting for the self-interaction given by the nonlinearities in the Einstein equation. Self-interaction between geometry and matter content, which end up defining regional backgrounds with their own content of quasi-local energy and angular momentum. This is a picture which is very different from additive gravitational potentials over a fixed Minkowski background. So we could ask, can perhaps a better implementation, a more nuanced implementation of GR affect how we estimate dark matter even in low energy regime for galaxies or galaxy clusters? Well, if we stick to galaxy, the answer that we can give is yes. To reach our answer, however, we have first to talk about past attempts, because there have been past attempts. Both Kopertsuk-Cantiel and Basil and Grumiller proposed already fully general relativistic galaxy models. The first, the CT model, was used to fit the rotation curves of galaxies far away from us, so rotation curve from redshift, while the BG model has recently been used to fit the rotation curve inferred for the proper motion of the star measured by the Gaia satellite. In both cases, if this model were completely usable with no issues, they will completely redefine our understanding of the dark matter content and of our universe as a whole. However, these models both ultimately fail and in our view are unphysical. Let's see why. Brief recap of our reasons. Both models present curvature singularities. The CT model on the galactic plane, the basic mirror model on the axis of rotation, away from the galactic plane. The CT model presents also exotic matter, so matter with negative energy, which is absent in the basic Miller model. And however, and both of them, most importantly, and regardless of their mathematical pathologies, some of which might be sidestepped by invoking the locality of the Einstein's equation, do present a very problematic feature, which is rigid rotation. They treat galaxy in an unphysical way by implementing a global description, which is rigid rotation. Galaxies are treated as rigid rotating bodies. However, as we know, galaxies are not rigidly rotating. Therefore, we must ask, can we do better? Can we find differentially rotating solutions to Einstein's equation which can describe possibly galaxies? The answer to this will be yes. So I told you that there are these models, that we want to build better models, but how do we do this? How was it done before? When we want to describe galaxies in general relativity, we must take an idealized version of the system. So we must discard morphological evolution, our system will be stationary, and we must not look for structure modeling, so no bars and no arms. Moreover, we will add, to simplify our calculation, reflection symmetry with respect to the equatorial plane, so that the model above and below, so that the galaxy, let's say above and below the equatorial plane, looks the same. Now, all these symmetries that we are adding in, so axisymmetric, stationary, are needed to try and even solve the Einstein's equation. For the highly nonlinear nature, makes them very, very hard to solve, well, basically. To finalize the description of the system, obviously we have to say how we describe the matter. And the matter of the system will be described within the perfect fluid approximation. Particularly since we are looking at self-gravitating system in which pressure should play an important role, the scales considered, galaxies, or possibly dark matter halo themselves, well, then we are going to use pressureless dust in geodesic circular motion. So this is how we build a model. Now, sadly, nice pictures are over, maths begins. So to describe the geometry of this model, we know the general form of the metric. It's known. This is the Lewis-Popper metric in which we see three different fields of interest. The conformal factor, which is related to the mass. This is a conformal factor on the space of the orbits. A dragging term, which is related to the rotation of space-time itself. And the classic pseudo-Newtonian potential, which informs us about in the post-Newtonian expansion and approximation about the classical Newtonian potential. Now, we described the geometry, the basic one at least, the metric. Let's talk about the source. The source, sorry, the source is defined through the prescription of a forward velocity, which depends on the rotational speed of the dust, that in BG and CT will be constant, but in our model is not, will depend on the current Z, and the normalization term, which is related then to the speed, the rotational speed of the dust, as well as the metric field. Through the forward velocity, the time-like forward velocity of our dust, we can then describe the energy momentum tensor, in which we will have the forward velocity and the effective density of our dust. Now, the effective density will have in itself also ingrained the quasi-local energy and angular momentum of the space-time and their coupling. It will account for that as well, since we are looking for exact solutions. So it will not be just the matter content, strictly speaking. Now, this metric is nice and all. If you try to look at the Einstein's equation, they're horrible. However, thanks to the work in the 70s of Garrosh and then on this specific metrics with dust of Weinkorn, we know that we can actually characterize this method through two functions of one variable each. First, we can arbitrarily pick the normalization factor as long as it's negative, and it is as a function of one single field, eta. Furthermore, we can choose a function that solves an harmonic condition taken back in the day as a Laplace equation and then related in a more complex way to h and eta. However, here we report it as a choice of a solution of the Grad-Shavronov equation, which is also used generally to describe, well, the non-homogeneous component of this is used to describe plasma in fusion reactors, which is pretty fun if you ask me. That said, the Grad-Shavronov equation wouldn't be reported in the work in the 70s. We had to work to reach this stage in recent years. So once we pick a boundary condition for the Grad-Shavronov equation, so for example, its value on the plane and the function of h, we can solve the Grad-Shavronov equation, and psi and h inform completely the metric, the system, through the nonlinear equation reported. Now, I've talked about the field eta, but I have not told you what eta is. So you might just be wondering. Now, eta turns out to be related to the velocity of the dust measured by zero angular momentum observer, ZAMO. Their velocity, this velocity, is what has been previously fit to the rotational curve of distant galaxies. However, in our work, we've proven that actually this is not the correct velocity to match to the direction curve. The velocity to match the direction curve should be the kinetic velocity, which is the one measured by stationary observer in the low energy limit. The two are related. The kinetic energy is equal to the kinetic velocity is equal to the ZAM velocity minus the dragging velocity, which is related to the rotational speed of the space-time itself. Now, I've said low energy limit. Why? Because it's time to use physics to inform our maths. Generally, the relation between psi, eta, and h will not be invertible. We won't be able to give a relation between eta in terms of psi, if not numerically. But we want to look for exact solutions which have a physical meaning. So we say, since we want to describe galaxies, or maybe even the dark matter halos, as it should be, dark matter should be non-interacting particle, therefore dust, and the halos should be rotating, well, then we can ask for what choice of eta would allow for a proper low energy regime limit. In this case, we find that eta is, as reported in the slide, should be of order 1 plus correction proportional to the square of the velocity, but h is a function of eta is proportional to the velocity, which means that h should be of the types -1 plus a term squared in eta. So if we take the first -1 and square and the term proportional to eta square, and we try to integrate and invert our relationship, we find out that we can. We can, and so we have obtained new differentially rotating dust solution. They are exact solution, and they are new. This solution gives us the relation between eta and psi, and very importantly, as we can see on this slide, through a relationship known between h and omega, so the rotational speed, they give us also directly our observable Vk. Now, remarkably, the request for a renormalization for a physical thing, therefore differential rotation, introduces a renormalization term in the definition of the physical relevant quantities, so that we can pick solution of the Grad-Shavronov equation, which are well behaved around the axis and that are renormalized at infinity. Now, we have said, now what we can say is that we have derived new solution, differentially rotating, which have a very clear physical meaning. They must describe the low energy limit of astrophysical system, which can be described by a coarse-grained dust approach in general relativity in a low energy regime, as said. Furthermore, these solutions introduce an other novel concept, which is the rotosphere. This is a new object that is found in this solution, a geometrical object previously not seen in GR. It can be understood in analogy to the Rindler wedge, as in it's kind of, but not exactly, an acceleration horizon, but not for linear acceleration, rotational acceleration. Furthermore, there is a clear difference between the two. One is given by particle emitted over a background and accelerated, but here the background is back reacting with the matter. So it's a different picture. We have a source there. Furthermore, our surface geometrically is rotating like an ergosphere, but it's not an ergosphere, for it does not encompasses a null horizon. Mathematically, it's the surface on which the density goes to zero before becoming negative, and therefore the point in which we hit the background in which what is left is gravitational, quasi-local sources of gravitational energy, and we're not looking anymore at densities, at real matter, real proper matter, but only the coarse-grained approach. On the same surface, we also have found the Ricci-Duri equation of the dust to be identical null with the scalar of the vorticity and shear that compensate each other. There are other properties we are still working out. As you've noticed, I have not been able to give you an archive number, but the paper over which this presentation is based should be on the archive by the time you see this presentation and should have been already submitted for publication. Now, to wrap up, we have found new solutions to the Einstein's equations, which, nice, they're differentially rotating dust solution. So they can be used to model system in which differential rotation is present, which are physical system, and they can be used to model, very importantly, low regime energy systems. So galaxies, dark matter halos, and others, as long as the dust approximation actually holds. Now, what does the future work for us entail? Well, understanding better, creating a framework to better understand how energy and angular momentum as quasi-local sources are produced through averaging procedure in general relativity. We need to introduce pressure in our system to model more complicated astrophysical systems, and we want to look and design for observational tests to prove or disprove the GR paradigm. Thank you for your attention.